Today's section is called the area of a region between two curves. And the start of the notes can be found on page 9. And your homework can be found on page 10. And it's these three cons. So we're looking at this essential question here. How is integration used to find the area between two curves? Now, we've talked about integration a lot. We know that when we integrate, we find the area of the region that is underneath that curve and trapped between that and the horizontal or the x-axis. So is finding the area then between two curves is just a slight modification of that. So this is not in your notes, but we're just going to discuss this. Obviously, you can't participate because we're not face-to-face right now. But we know that the definition of the definite integral says exactly what I just said here, is that if we take the definite integral, so that's integrating the function f of x between a and b, so let's set up a and b. So if we integrate this function between these two things, the definition of that, the definition of this definite integral here says that this value captures the area between the function and the horizontal axis. So that's that green region. So the value of that region between the function and the horizontal axis is the value of that definite integral. So that's the definition. And we're going to use that definition so that we can find the area between two curves. So we have to develop that strategy then. What happens when we introduce a second curve? So this is where your notes kind of begin here. So here's that same function, f of x. And that we know that when we integrate f of x from a to b, that we get this green region, we get the value of that area between the function and the x-axis. So let's introduce a second function here. Let's introduce g of x. G of x is also between a and b. And so if we integrate g of x between a and b, we get this red region between the function and the x-axis. So if we superimpose them, now we have two curves on the same grid. And so the area between these two curves then is just the green minus the red. So it's quite literally f of x minus g of x, integrating f of x minus g of x between a and b. It's essentially saying let's integrate f of x, get that whole green region. Let me back step here. Integrate f of x, get that whole green region. Integrate g of x, get this red region, and subtract it. Take it away because we don't want to go all the way down to the axis anymore. So, so that is the strategy for finding the area between two curves. And the nice thing is it works even if g of x is beneath the horizontal axis. So here's our same f of x. Now let's introduce g of x. And all I did was shift g of x down. It looks like I shifted it down 1, 2, 3, 4 boxes. And so now f of x is, if I integrate f of x between a and b, I get the green region. If I integrate g of x between a and b, I get this region here between the function and the x-axis, so this red region. And if I subtract those, because this is a negative region, if I take green plus a negative, or green minus a negative red, that ends up being an addition process. So the general statement here, f of x minus g of x from a to b, still holds true. Because when I subtract g of x, let me just backspace again, the integral of g of x is this red region, and we know that when we integrate something beneath the x-axis, we get a negative value. So if integrating g of x gets to be negative, then this ends up being, after we integrate it, f of x plus g of x, which is this whole blue region, this green plus red. So there's the statement then for finding the area between two functions. Okay, now these functions, we call them top-bottom functions because we have one on the top and one on the bottom. And by top, I mean f of x has bigger y values than g of x does. And if you notice, from a all the way out to b, f of x is always the top function, and g of x is always the bottom function. In other words, they don't cross. That's a whole different section of content. So to find the area between two curves, we just are going to take that top function minus the bottom function, and we're going to integrate it from a to b. And that answer will always be positive because of what we talked about, the definition of the definite integral, that this being the lower curve, even if this is negative down the fourth quadrant, minus a negative is positive. And we are talking about area. We know back from geometry that area is always a positive value. Okay, so we're going to focus on looking at these. We've got two examples that we're going to really focus on. And so we're going to kind of work with this strategy here, finding the area. So the idea is we want to get a sketch, and we want to identify the region, just like we did back on the previous page with the blue region. We want to find any points of intersection if we have any. Like we haven't, like for this one, f of x and g of x don't intersect. So that wouldn't apply anyway, but sometimes it does. Step 3, writing an expression for the area. That's our f of x minus our g of x. And then identifying the limits of integration, step 4, like for this one would be 0 to 3. That's just going to set up our upper and our lower bounds. Step 3 and 4 combined is what we call the setup. Okay, I'll talk more about the setup as we go through examples. And then we have to go through the calculus. We have to integrate that expression and evaluate it, plug in the bounds and all that stuff. And that's called solving. So when we talk about setting up and solving, we're talking about these steps here, 3, 4, and 5. And sometimes we're asked just to set something up. Sometimes we're asked to set it up and solve it. So let's take a look at these examples then. So example 1 here says, let region R, it's right down here, it's gray, be the region enclosed by the graphs of f of x, which is 4 minus x minus the quantity x minus 1 squared. So it's parabolic. There it is. And g of x. G of x is minus 2 minus cosine pi over 3x. So it looks like that. So it's the region between these two and the y-axis, which means it's going to start here. That's going to make our left bound or our lower bound. And the vertical line x equals 3. So that's over here. That's going to be our right bound or our upper limit. Okay, so if we notice we have an f of x and a g of x, we have an upper or a big function, and we have a top function. We have a g of x or a lower function or a bottom function. And then this last statement here, the y-axis and the vertical line x equals 3, that's another way of setting up your bounds, your limits of integration. So let's go for the setup here. Write an expression for the area. So we know that f of x is the big function, so it's the top function. So the expression is going to be f of x minus g of x. So that's the expression for the area between those two functions. And then we know that we have to then identify the limits of the integration. So we're going to plug in f of x. We're going to subtract g of x. Notice the use of brackets here. I'm not being skimpy with the brackets. I put f of x in their own bracket. Then I have the minus sign, and then I put immediately a bracket here. I put g of x in its own bracket because we're going to have to distribute that minus sign. And that's a big deal here because that changes those signs each and every time. And then we've got to, so that's the writing of the expression. Now we've got to identify the limits here of integration. So we're going to put our integral sign here. We know we start at 0 and go to 3. That's these two pieces of information. And then we're going to cap it off over here with the dx. So there's the setup. So when you're asked to set up an expression, that is all you have to do. And you're done with the question. This is a setup and solve because we are being asked to find the value of the region. Okay? And so we're going to have to set up and solve this. So let's start the solving process. So the first thing we want to do is we want to clean this up a little bit because there's a lot going on there. So we're gonna go ahead and start solving here. So I'm just gonna start integrating from left to right. And we're gonna kind of brush up on our integration techniques, especially for the trig stuff. So the antiderivative or the integrating 4 gives us 4x. Then we get a minus sign here. Now I have to integrate this. So I'm gonna bump up the power to a 3 and divide by 3. So bump up the power to a 3 and divide by 3. Okay, so there's the antiderivative of that. Then I've got a minus sign here. I'm going to cap that off with a nice set of brackets. I'm going to bring my minus sign down. I'm going to integrate the minus 2. It becomes a minus 2x. I'm going to integrate minus cosine. So minus cosine goes to minus sign because integrating cosine goes to sine. Pi over 3x. But then remember, we have to divide by the derivative here. So we have to divide by pi over 3. Okay, so there's a lot going on here. Let me cap these off with some brackets. So let's just kind of review what's going on here. I integrated the 4. I integrated this. This is a u sub, but it's linear in here, so we can just do the power rule on the outside. Bump it up by 1 to a 3. Divide by 3. Divide by that new power. Derivative in here is 1. We don't have to divide by the 1. That won't change anything. Okay, integrated the negative 2 for negative 2x, integrated the cosine to get a sine, and then all the stuff inside here just gets duplicated down here, but then we have to divide by that derivative, and the derivative here is pi over 3. Okay, so now I haven't put on the limits of integration yet because I still want to clean this up. This is pretty clean. I'm going to, instead of dividing by pi over 3, I'm going to multiply by 3 over pi. So all I'm doing is a little bit of cleaning up here, just so that it's easier to work with. Okay, so I'm going to change screens now, and this is going to appear at the top of the screen. There it is. Nothing changed there, though. So I'm going to keep cleaning this up a little bit. I think I'm distributing the minus sign here. So I got a plus 2x, and I got a plus 3 over pi sine pi over 3x. Now I'm going to slap on those limits of integration. Now we can go ahead and process the upper and the lower limits. So there's the antiderivative. I'm going to plug in the 3. So I get 12. When I'm doing the math as I go along, I got a minus sign here. Now I'm going to plug in the 3 here. So I've got 2. 3 minus 1 is 2. 2 cubed is 8. So this whole thing is 8/3. I'm going to put my plus sign down there. 2 times 3 is 6. I'm going to put my plus sign there. 3 over pi sine, and then when I put a 3 here, I just get a pi, right? Because pi times 3 divided by 3 is just pi. I'm going to cap that off with a nice set of brackets. That's plugging in 3 everywhere. Now I'm going to plug in 0. So minus, and now I'm going to plug 0 in everywhere. So this is nice. 4 times 0 is 0. I put a 0 in here. And this becomes a negative 1, and when I cube it, it's a negative 1. So I have a negative 1/3, but I have a minus out here. So I have minus negative 1/3. That turns into a positive. I plug in 0 here, I get 0. I plug in 0 here, I get sine of 0, which is 0. So this whole thing becomes 0. Okay, so that's really nice. Okay, so now I can start evaluating. So sine of pi is 0. That's over on the left-hand side of the unit circle. Sine of 0 is 0. That's really nice. So I'm left with 12 minus 8/3 plus 6. And then coming over here, minus 1/3. And then everything else is 0. So we've got 12, and then if I take the two fractions here, that's minus 9/3, which is 3. So 12 minus 3 is 9, plus 6 is 15. So the answer is 15 square units. So that's the area of that region R. Okay, so that's all. That was a lot of integration, and all by hand and everything. And sometimes they ask you to do this by hand. Sometimes they let you use a calculator. So this is a calculator active question. So let's take a look at what's happening here. So we have this calculator active question. I can't remember the year this was from. I think it was like 2016, 2017, so pretty recent. And a question like this is a sure bet on the test to ask you to find the area between two curves. Whether it's by hand or on a calculator, that's pretty much a crapshoot. But it's a sure bet that they're going to ask you to do one of these on the free responses. And there's a sure bet where it's going to involve, a chain rule on the integration if they make you do the integration, like this here, where we had to divide by the pi over 3, that sort of thing. So we got to put those in as much as possible to get you really comfortable with that. So this one says find the area of region R. So let region R be bounded by the graphs y equals sine pi x and the graph x cubed minus 4x as shown in the figure. So it's calculator active, so you might look at this figure and you might think, well, which one is which? So remember, sine oscillates, so that should help you figure out that the top one here is the sine of x, and that leaves the bottom one to be the cubic. Okay, so we know that the sine function is the top, or the big function, big y values. This is the bottom, or the small y value, so it's going to be sine pi x minus x cubed minus 4x. So now this is really interesting because this is verbatim taken off the AP exam. Find the area of R. Okay, this implies two things: setup and solve. So if you remember, we go back to those 5 steps for our strategy. You have to do steps 3 and 4 and 5. And so, but using the calculator, the solve part becomes all calculator based. It all becomes a math 9. But they do grade your setup. And so this tiny little 4-letter word means a lot. So let's talk about that setup. That setup is just writing the expression, right? So we start out by saying we're finding the area. So area equals. And we know that the top curve is sine pi x. And we have to subtract the bottom curve, which is x cubed minus 4x. And again, I can't stress enough, be really generous with using lots of brackets, so that we remember to distribute that minus sign. We're going to put our integration sign out front, and then we have to find our limits of integration. So this is called a bounded or enclosed area. In other words, we have points of intersection here that close off the shape. So the left intersection point is at 0, and the right intersection point is at 2. And that's pretty obvious from the graph here. But if it wasn't obvious, then we'd have to set this function and this function equal to each other and solve for those values. So here is the setup. So this is going to get you your setup points here, where we have the 2 functions with the minus sign and everything nice and bracketed off. We've got a lower and upper bound and a dx. Okay, so now we're going to take this and do an int on our calculator. Okay, so we're going to try to do that right on the screen here. So we don't need to even graph it if we don't want to. We just need to do a math 9, and we're going to go from 0 to 2. And then again, I'm going to be generous with the brackets. It is sine pi x. I'm going to close off the pi x brackets and close off the sine brackets. And then minus, get myself set up with some more brackets there because I like to be generous with those. And then the next function, the bottom function, was x cubed minus, whoops, I can't put the minus there, let me get rid of that, minus, and what was it, 4x? Let me go check, I can check that. X cubed minus 4x, yeah, that's what it was. So x cubed minus 4x, and then I need to close off the g of x brackets there. So I've got sine x in its own brackets. I've got, so this is f of x, and this is g of x in its own brackets. And I'm going to cap it off with my dx on the end. So there is the math 9, or the f int. And when I hit enter, that area between those two curves must have a value of 4. So I'm going to go ahead and come back here I did an F and int on my calculator. Do not show what shows up on your calculator screen. Don't put that in your test booklet. You need to put this notation in your test booklet. But then, I didn't check it, but I know I'm in radian mode in my calculator. So let's just go back and show how you verify that. Here's the mode key right here, and then you have to be sure it says radian, not degrees. And then leads to an answer of 4. So when we're on a calculator active question, we show the setup, we let our calculator do the work, and then we show the answer. And that's how we get the points there for a calculator active question. This one can also be done by hand, so let's kind of really quickly go over this. So area equals, let's integrate this. So the integral of sine, if we integrate sine, we get negative cosine. Oh, I'm cleaning it up first. I'm sorry. I see what's going on. So what I did here is I distributed the minus sign. I haven't done any calculus yet. So I still have to integrate from 0 to 2. I just wanted to get rid of some brackets here and make it a little more clear. Now let's go ahead and do the antiderivatives here. So this is minus, the antiderivative of sine is minus cosine. So this is minus cosine pi x. Then I have to divide by the pi, right? We have to do that chain rule in there. And then the antiderivative for x cubed is bumping up the power to a 4 and dividing by 4. So x to the 4th over 4. And then integrating 4x is bumping up the power to a 2 and dividing by a 2. So we're going to simplify that. And so that's minus cosine pi x over pi minus x to the 4th over 4. And then this simplifies to minus 2x squared. Now we can go ahead and plug in the limits of integration from 0 to 2. So when we look at that, from 0 to 2, let's plug in 2. So we plug in 2, we get minus cosine of 2 pi over pi, 2 to the 4th over 4, and 2 times 2 squared. And then when I plug in 0, so cap all that off with a nice set of brackets, that's the 2's everywhere, minus the 0's everywhere, so cosine of 0, 0 to the 4th over 4, 2 times 0 squared, cap those off with nice sets of brackets. So now we can really go for evaluating this. So 2 pi, that's the same as 0 on the unit circle, so we know this is 1. So that first term is minus 1 over pi. 2 to the 4th is 16, divided by 4 is 4, so we know that's minus 4. 2 squared is 4 times 2 is 8, so it's plus 8. And then over here, we know that cosine 0 is 1. So we're going to have minus a negative, so it's a positive 1 over pi. And then the remaining terms are 0, so I'm not even going to look at those. So if you notice the 1 over pi and the negative 1 over pi, they cancel. We have minus 4 and plus 8, and that makes 4. So this we kind of verified this using Math 9. We got the same answer as 4. So it's not too bad to integrate by hand. And then the last example is just part B. They say, let's take this same shape and let's draw a horizontal line at y equals negative 2. That's down here. And they're telling you, they love to tell you what to do. They're telling you they want you to draw a horizontal line, and here's where they want it to cross the y-axis. So you're going to come down here and draw this line across the region. And it says it splits the region into 2 parts, which it does, an upper part and a lower part. It's write but do not evaluate. So that's another way of saying, I want the setup, but I don't want you to solve. So this is a setup question only. Write but do not evaluate an integral expression for the area of the part of region R, so we're only talking a part of this, below the horizontal line. So that is right here. So in other words, it's this region down below that is between the blue line and the green curve. So if that's the case, then this blue line makes the top function and the green curve makes the bottom function. So the setup then involves writing it this minus this, and then we have to find these points of intersection. Okay, so we have to find those 2 points right there. So in order to do that, that means we have to graph these, because we could set x cubed minus 4x equal to -2, but I think that would probably be really hard to solve. So we're going to do that on our calculator. So that was x cubed minus 4x. So now I'm going to start to use my y equals. So I'm going to put the x cubed minus 4x into y1, and I'm going to put -2 into y2. And those are the only two things I need. So that's going to be down there. So I am going to change my window all the way out to 3. And I think those look okay. And we could even draw in, if you wanted to, we could even draw in that sine pi x, even though it doesn't factor into this part of the question. So we've got that, right? So this is the region R, but we're concerned about this stuff. I'm just going to tweak that window, that by min down to -4, just so we get the whole picture here. So we need these 2 points of intersection here. This top curve isn't going to come into the picture because it doesn't intersect it. So remember, that's a second calc intersect, second calc 5. And so I'm going to first find the one on the left. So notice it's saying first curve, question mark, and it's blinking on the x cubed minus 4x. So I'm going to hit enter to confirm the first curve, and it jumps to the second curve, which is my -2. So I'm going to hit enter again to confirm, and then it wants me to guess. So I'm just going to hit enter for a third time to confirm, and it's going to find that intersection. So we know that intersection is 0.539. That's going to be my lower bound. Okay. And then now I'm going to repeat the process for the point of intersection over here. So I am going to scoot over close to that point of intersection and then do a second calc again, 5 for intersect. Oh, I guess it put me back there. Okay, so now I'm going to scoot over by using my arrow key. So I'm going to pick the first curve, which is the blue curve, and then the second curve, which is the red curve, and then my last guess here. And so that point of intersection is 1.675. That's going to be my upper bound. So we're going to take those into our integral expression. So our area then is going to be my upper curve, -2, minus my lower curve, x cubed minus 4x. And we're going to integrate between those two bounds, a and b. And notice the a and the b, I located the a and the b and I noted it on the graph. And I said a equals 0.539 and b equals 1.675. If you identify what a and b are, you can use the variables a and b in your expression. That's perfectly okay. The other thing you could do is you could put the 0.539 here and the 1.675 up there. So this is the setup. This is the write the expression, but do not evaluate it. So that's all we have to do for that problem is just the setup, and we're done. If you wanted to do an FN int on this, the answer would be 0.811. If you just wanted to check your ability to calculate the correct answer. Okay, so how is integration used to find the area between two curves? The area of a region is found mathematically by taking the upper curve minus the lower curve when you integrate. So it's just a matter of kind of extending that idea about the area being between the curve and the x-axis. So you should be able to do the 3 homework assignments now. The first one is just typical integration between a curve and the x-axis like we've done all the time. The middle one is the area between two curves given endpoints. So those two curves are open on the ends, and then the last one, the area between two curves, is where it's an enclosed region. So you might have to find the endpoints by either doing a second calc intersect like we did, or by setting the functions equal to each other and solving for x.